So let's throw a little trigonometry in here, and we'll look at this more closely probably tomorrow. Let's find the limit as x approaches 0 of the sine of x over x. And usually the first thing I do is I cheat, see if I might get lucky. And if I try to cheat here and plug in x equals 0, then I'm going to get the sine of 0 over 0. And we always get this thing in math, you can't divide by 0. I talked about why you can't divide by 0 in a class last week. Sine of 0 is 0, so this is 0 over 0, which means there may be a limit. And just a reminder on what the word limit means here. And limit exists only if we approach a real number. And we'll look at in a moment what it means to not approach a real number. Okay. So 0 over 0 is what's called an indeterminate form, meaning with more explanation, 0 over 0 may resolve to be a particular number, like 20.086 about, or pi, or 4. Right? We've seen a couple of different examples now. What's happening with this one? Graph is a nice thing to look at next, and then if the graph's not particularly helpful, then we can look at a table of values. So let's reload Desmos. I don't need that stuff at the moment. Come on. There you go. And let's give it a name, f of x for lack of imagination, and the sine of x divided by x. So looking at the graph, it looks like there's an answer right there, okay? And if I point to it, I can get near it, but not at it. Now notice if we zoom in here, it is giving us an x-intercept, it's giving us what it believes to be a minimum point, another x-intercept, but it's unable to give us a y-intercept because f of 0 does not exist. There is no point when x is 0 on this graph, but when I zoom in there, looks like there ought to be a point, but there's not. There's a little microscopic hole there, only at 0. And we can figure out where that hole is if we look at numbers close on each side. We could do that right here. We could build a table. Maybe I haven't done a table in Desmos in a while. Where's that button for a table? Right there. Table. Okay. And then up here, I can edit that y and put in my expression as the sine of x. And I've got to call it x1 because that's what's in the column to the left, divided by x1. And so when I plug in a number here for x1, it should give me the y value next to it. So if you don't like using a spreadsheet, you could try this, 0.1, 0.00 or 0.1, 0.0001, oops, too many zeros, and look on the other side, make sure it matches. Now the graph looks like it should match, but I don't know. Negative 0.1, negative 0.01, 0.001, and it looks like, yeah, it looks like we're getting closer to 1 each time. Eventually, I'm going to exceed the computer's ability to calculate this. So if I put too many decimals there, it's going to say, that's 1. But we know it's not 1. It's just close to 1, and the computer said, there's too many 9s there, it rounds to 1. So looks like numerically, and evidence is in our calculator, the limit as x approaches 0 of the sine of x over x is equal to 1. Now, when I put equal to here, it's a little different sense of the word equals than like 2 divided by 2 equals 1, okay? In this case, again, it's approaches. So the proper way to read all this, even though I put an equal sign there, it's a little bit different context, as x approaches 0, the sine of x over x approaches 1. In this case, it doesn't actually get there. There is a hole in that spot on the graph if we consider this a function y equals sine of x over x. So does the sine of x over x ever equal 1? The answer is no. Does the limit as x approaches 0 of the sine of x over x equal 1? The answer is yes, and this is what yes means right there. Okay, so we're using equals in a slightly different context than we used to. Another thing to point out about this example and some of the other ones. When I look at a limit, usually I'm approaching from either side. So the idea that as x approaches a number, let's say, I guess it was 0 a minute ago, x can approach from the right or the left. So we can, because we're on an axis, approach from two different sides. Sides. So something like the limit as x goes to 0 of some function of x, this right here is called a two-sided limit because I'm not saying I'm on the left side or the right side as I approach. So two-sided. So we also have a right-sided limit. And that would be the limit as x approaches 0. From the right, we put a little plus, kind of like it almost looks like it's supposed to be an exponent there of f of x. So that means we can only use x values to the right of whatever number I have there. And then we have a left-sided limit. So that would be the limit as x approaches whatever number on the left side. Now, in this case, they are literally positive and negative, but that's not always the case, as we saw in previous examples. Like I was on the left of 2 and the right of 2 for one of the examples I was looking at before. And as far as the left-sided and the right-sided limit in relation to the two-sided limit go, if the left and the right match, then the limit as x approaches 0 has a limit. So this is an important rule. So if the limit as x approaches some number of a on the right side of a function is equal to the limit as x approaches a on the left side of that same function, and let's say they're equal to the same number L, then we can say the two-sided limit, if I don't reference a side, no plus or minus there, then I can say that is some number. And remember, L is a real number. So we need to look at some cases where limits don't exist, meaning L is not a real number, and there's several ways that can happen. We looked at a couple last week. I'll remind you of those today and a few other ways. Let's see, reset this. We're done with that one. So let's look at, let's call it R of x for rational function equals 1 over x. We took a look at this one last time. And if we tried to let x equal 0, right, R of 0, you might look at me and say, why would you plug in 0 here? You can't plug in 0. Well, sure I can. I can try, and I get undefined, no answer. And we can see on the graph that it looks like when we scroll up, it's not touching the axis. Eventually we lose resolution and they kind of merge together, but that's a computer visual issue. So we are looking at the limit as x goes to 0 of the function 1 over x. And when we try to cheat, right, 1 over 0 does not exist. And this is different than 0 over 0. 0 over 0, there's a hope for existence. 1 over 0, there is no hope for existence. No hope for a limit. And I can explain later why 0 over 0 has hope, but 1 over 0 does not. Again, if anybody wants, in a discussion last week. So what we need to do is look at each side to explore more carefully what's going on here. So what's happening is that x approaches from the right side of 1 over x. And we could make a table to see what happens there. And this is something hopefully you did in a college algebra or algebra 2 class sometime in your past. So numbers like 0.1, 0.01, 0.001, and this is slang for reading these numbers, that's 1/10. And if I take and I flip 1/10, oops, I get 10. And if I flip 1 over 1/100th, I get 100. And the same thing here. If I flip that, I get 1,000. So if I plugged in 0.0000001, 2, 3, 4, 5, 6, this is tenths, hundredths, thousands, 10,000, 100,000s, millions. 1 over that would be equal to 1 million. Oops, one more 0. There we go. And so what it looks like as x approaches 0 from the right, 1 over x increases. And it looks like it increases forever. So this keeps getting bigger. So this right here is heading to 0, but positive. And this over here looks like it's going to infinity. So I can write the limit as x goes to 0 from the right of 1 over x is equal to infinity. But there's a catch here. Infinity is not a number. So technically, this limit does not exist. Infinity is not a number. So this is one way a limit can fail to exist. Infinity ain't a number. If I look at the other side, if I take the limit as x approaches 0 from the left side of 1 over x, then in that case, I have numbers like -1/10 and -1/100th and -1,000th. Oops, too many zeros. And -1 millionth. 1, 2, 3, 4, 5, 6. And the y value in this case will be -10, -100, -1,000, -1 million. And so in this case, as x approaches 0 on the negative left side, the y values are decreasing forever. So formally, so I can write something like the limit as x approaches 0 from the left of 1 over x is equal to -infinity, but here I'm using equals in an even different sense than I was when I talked about the limit that did exist. Technically, what I'm saying here is that as x approaches 0 to 0 from the left side, 1 over x is decreasing forever. And again, -infinity is not a number. this limit does not exist. Oops. Even though I'm saying it's equal to something, it's not a number, so it's just a fancy way of saying it's not exists. So sometimes I can say, instead of just saying, hey, this limit doesn't exist, I can at least give you some more information. I can say, hey, that drops forever. That's information. It's a way of not existing. It's important information about the graph. And when you were doing college algebra, you talked about this was end behavior. So this idea right here describes the end behavior. So the limit doesn't exist. Okay, that's true. But at least we have some information about the end behavior. Of the graph. Another thing to consider is if we tried to just reference the two-sided limit that I had back here, there's nothing I can say about this except like if the computer had a box here and it wanted an answer, the best I could say is does not exist. I can't say positive infinity because that's only on one side. I can't say negative infinity because that's only on the other side. So in general, for the two-sided limit, the best we can say is does not exist. Another way something cannot exist is by just not settling down. So let's look at a limit at infinity. In a slightly different way, infinity. This time, let's let x do the infinite thing. So let's let x grow forever. And the function we'll look at is the sine of x. So what do we know about the sine of x? Well, think back to your trigonometry days, which was probably very recently. We know that the sine lives between 1 and -1. And you have a bunch of values in the unit circle that you've memorized, and the graph is a cute little wave. So let's look at that little wave. Let's get rid of this guy. Let's see, I probably should zoom which way? This way. I totally messed this up. Let's reboot. Call this S of X for sine. And so we know it oscillates and it periodically has a peak, right? Starting at pi over 2, every 2 pi later, it has another peak. So pi over 2 plus 2 pi is 5 pi over 2. If we were to try and make a table here, let's add a table just for fun and watch x get big. And over here, we'll get rid of that y1 and we'll call that the sine of x1. And if I want to do a calculation, whatever input variable is here has to match here. And so I could do like plug in 10, 100, 1,000, 10,000, 100,000, and even 1,000,000. And I can see that I'm all over the place with the y values. And I kind of already knew that because of the way the sine oscillates based on how it's related to a circle. So in this case, it never settles down as my x values increase. Now I could accidentally deceive myself in a table like this. So if I were to only plug in numbers related to this pi over 2 right here, then I might always get a 1. So it is possible that we accidentally pick a sequence of numbers that misleads us here, right? So for example, if my sequence was like pi over 2, and then 5 pi over 2, and then 9 pi over 2, and then 13 pi over 2. I could accidentally mislead myself. So we do have to have a little bit of caution when we make a sequence of X values heading towards some place. I could easily mislead myself. So looking at various sequences numbers, eventually I'm going to convince myself that as I look to the right, this is always oscillating in exactly the same way, and there is no limit. So in this case, the best I can say here is that this limit does not exist. And if I needed a reason, I could just say since sine of X is periodic. Oops. Pi y is always between -1 and 1 as X increases or decreases, but I'm only looking at increasing here because of the infinity. Okay, so this limit does not exist. So there's multiple ways a limit cannot exist. It heads to infinity, it heads to negative infinity, it goes two different directions, it oscillates forever. So let's look at one more of these. Kind of reversing it. So in the last example, right, I had X was going to infinity over here. Now, if I flip infinity, which kind of relates back to this right here, if you try to divide by 0, you approach positive or negative infinity depending on the size of the numbers. And if you go the other way, if you try to flip infinity, you get closer to 0. And so I'm going to come back to the sign in a second, but let's look at the limit. Another in X goes to infinity of 1 over X. What happens here? Now, we can't just cheat and plug in infinity because infinity ain't a number. So that's not going to work. So our only course of action here is to make a table and compare X to 1 over X as X gets big. So this says again, as X, the correct way to read this is not as X approaches infinity, but as X increases forever, or sometimes we say without bound. What is 1 over X doing? So we could go 10, and 100, and 1,000, and 10,000, and so on. And when we flip those numbers, we get 1/10, and 1/100th, and 1,000th, and 1/10,000th. So as these X values get bigger, forever, these Y values over here seem to be approaching 0. But notice, since I'm plugging in a positive number, the reciprocal is always positive. So we're approaching 0. We could say from the right side, but really it's from above in this case. And we know what this graph looks like. You've studied it. And let's reboot. X. And so we're plugging in bigger and bigger numbers here as we move out. And we know that this is an asymptote. So asymptotes are an important part of the limits. And so we've looked at a couple of them here. So this is like the definition of a horizontal asymptote. So it goes to 0. So I can say the limit as X increases 1 over X equals 0. Now again, equals, do we ever get to 0? The answer is no. This is all about approaching. So as X increases, so we have a different sense of 0 again, so we kind of have to lower our expectations a little bit. We don't actually get that number, we just get close to it. So without bound, then 1 over x approaches, but doesn't get to, ever 0 in this case. And this is the definition of a horizontal asymptote. So you've studied these limits before in other classes when you looked at horizontal asymptotes, when you looked at rational functions that had holes in them because of a 0 in the denominator that matched a 0 in the numerator. And so we're just defining them a slightly different way and using a little bit of different notation. All right, I think we have time for one more example. Let's take a look at one of the homework problems that I can't easily draw. Actually, I can, just not easily. Oh, I said I would get back to the sine of x again. Yeah, so I wanted to combine for that example, this one right here with this one right here, putting them together. So if I flip x, infinity turns to 0 and 0 turns to infinity. Is kind of what a couple of these examples get at. And so what I want to do is look at the limit as x goes to 0 of the sine of 1 over x. And the key thing here is x is going to 0, so 1 over x is getting either infinitely large on the right or infinitely small on the left. And this is a funky graph. Let's take a look and see what happens here. Sine of 1 over x, and oops, extra parentheses aren't necessary. Go, and let's get back. Whoa, so check this crazy stuff out here. What's happening in here? So think about the sine of x, right? What I've done is I've flipped the domain by doing a 1 over x instead of an x. So what used to happen with the sine, let's graph the sine at the same time, and the pivot is at 1, the pivot point. So notice that these two are equal at 1, right? They intersect there. And we looked earlier at what happens if we let, for the sine of x, the blue wavy thing, what happens as x goes to infinity? Well, it just oscillates regularly forever. By flipping x here, what we've done is we've taken that infinite oscillation and we've crammed it between 1 and 0. So by replacing x with 1 over x up here, we took the x values 1 to infinity and squeezed them in between 1 to 0. So that infinite oscillation has to happen faster and faster and faster and faster as you get closer to 0. And so because of that infinite oscillation happening in here, this thing is never, ever going to settle down. It's going to oscillate faster and faster and faster as you zoom in here. And let me see, GeoGebra might do a better job of graphing this. GeoGebra, because I can stretch the axis in a slightly different way. Let's see, how do I do that here? I switch to the move tool, and then I think I can just grab the axis. Is it going to let me do it? Oh, come on. You still let me do it. Settings, x-axis. Change the way it works. 0.01. No, maybe I want the grid. Basic. Used to be able to click on the axis and drag it, but they've changed the behavior. So let's go from 0 to 1. And so we've got this oscillations. You can see that they're increasing there. And if we try to zoom in again on that in the grid, what if I went from 0, we're going to lose the ability to calculate really quick on this one, 0.1. It looks almost the same as I zoom in. Oh, nope, there we go. It took a while to calculate. So here we go, that's what I'm trying to show. Oh boy, I think I broke it. It won't close. So again, see that infinite, that oscillation getting faster and faster and faster as we move towards zero. So there is no limit here. Limits can get really weird. Most of the stuff we've looked at in pre-calculus, pretty straightforward stuff. But this one, all I can say is it does not exist because we have these oscillations going on. Increase towards x equals 0. So this was section 2.2 that we were going over. Tomorrow we will play around with some rules to help us more quickly evaluate these limits. And then that'll be the rest of the week relating this to what a continuous graph is versus a discontinuous, and then the formal idea of a limit. That is really wild and quite challenging. So if you haven't already, read section 2.2, start reading section 2.3, because we're going to start section 2.3 tomorrow. If you have any questions, send me an email or message me through the homework system. Take care, do good math, and I will see you all tomorrow. You're welcome. Take care.